optimum process chain consisting of 2 units was created to verify the technology for separating tritium from liquid radioactive wastes, or LRW. The first unit is the tritium-containing distillate preparation unit, and the second is the tritium isotope separation unit. 50 cubic meters of a simulated solution identical in radionuclide and chemical composition to the accumulated LRW containing tritium from the Fukushima 1 nuclear reactor was produced to verify the technology. The simulated solution was completely demineralized in the Ross-Rao evaporator to prevent the accumulation of salt residues in the isotope separation process equipment. The salt residue was solidified in asphalt and sent for storage. "48 cubic meters of tritium-containing distillate from an A50 drum is transferred to the newly constructed second unit building for isotope separation. The new building is divided into 2 spaces. The first is the process space with a top level of 10.5 meters. The second single-story space is the auxiliary space, where the utility systems are located. The process space is divided into 3 units. The tritium is separated from the LRW in the water distillation unit, with a separation factor of 500 and a concentration factor of 40, with a capacity of 200 liters per hour. The tritium in the water is concentrated 500 times more in the concentration unit, with hydrogen capacity of 8 cubic meters per hour. The tritium is rendered safe, fixed in solid titanium hydride in the fixation unit. Let's take a look at the water distillation unit. Here, the intake stream is purified by a factor of 500 in the water distillation column. The column consists of a side-mounted evaporator, the column bottom, 10 shells with packing, and a condenser. The height of the column with the condenser from the support sleeve is 43.5 meters. The column is connected by a steam line to side-mounted evaporator P91. This is located at the level of the column bottom. The evaporator capacity for steam-containing tritium is up to 6,500 kilograms per hour. Heating steam is fed to the evaporator at a maximum flow rate of 6,500 kilograms per hour and a pressure of 4 megapascals. The flow rate is maintained accurately to within 3% using an automatic throttle valve at the evaporator intake, with a response time of less than 1 second. The evaporated steam containing tritium is fed to the upper part of the column bottom through a pipe 300 millimeters in diameter. The condensate is removed from the lower part of the bottom. The capacity of the condenser installed in the upper part of the column is up to 6,500 kilograms per hour of steam condensate. The condenser is cooled by process water at a flow rate of 130 cubic meters per hour. The cooling water arrives from the cooling towers at Ross-Rao at a temperature of between 15 and 30 degrees centigrade. Cooling towers are not required for the full-scale unit, since a system with heat recovery from the condenser to the evaporator will be used. The evaporated water arrives for phase isotope exchange from the packing part of the distillation column. The water vapour is depleted of tritium as a result of contact with the liquid flowing down through the column. Flow distributors with 5,000 pour points are installed in the lower part of each shell. With the selected process parameters, the tritium content in the vapours and in the liquid in equilibrium with them in the upper part of the column is reduced to roughly 10,000 becquerel per litre. While a concentration of tritium-containing distillate of the order of 2.5 times 10 to the 8th power becquerel per litre is achieved in the lower part of the column. The water distillation column operates under rarefaction. This is provided by vacuum pump P131 with a capacity of 60 cubic meters per hour, connected to the condenser by a pipe 100 millimeters in diameter. Heat exchanger P151 to cool the vapor gas mixture and receiver tank P121 to smooth the pressure surges are installed in the vacuum line upstream of the pump. The maximum allowable working pressure deviation is 3%. This is maintained automatically. Sampling from the column is performed at 2 points. Purified water is sampled from the upper part of the column, while water enriched with tritium concentrate, is sampled from the bottom. 6.15 litres per hour of tritium concentrate is fed alternately to tanks P31 and P32. This is required to take the control measurements of the tritium activity. Then the concentrate arrives at tank K11 in the final concentration unit. This is the feed tank for the next stage of separation. The purified water is fed at a flow rate of 197 litres per hour alternately to tanks P101 and P102, which are installed in parallel. The parallel installation is necessary to monitor the tritium concentration in the purified water prior to discharge. When the tritium concentration meets the standards, the purified water can be discharged from tanks P101 and P102 to the Ross-Rau process water supply system. Condensate collection lines also run from heat exchanger P151 and receiver tank P121 to these tanks. From tank K11, the intermediate concentrate with activity of 2 times 10 to the 8th power becquerel per litre and flow rate of 6.15 litres per hour obtained in the water distillation unit arrives at the upper part of the chemical isotopic exchange column K31. Here, the tritium primarily changes from a gas to a liquid. We obtain tritium-enriched water at the bottom of the column and hydrogen depleted of tritium at the top. The column operates at atmospheric pressure and a temperature of 60 degrees centigrade. This specified temperature is maintained by electric heating. The air is expelled by argon from the column and equipment prior to startup to prevent the formation of an explosive air-hydrogen mix. The tritium concentration process in this column occurs due to chemical isotopic exchange. Water and hydrogen interact, and hydrogen is obtained from the same water by electrolysis in the bottom of the column. The column contains packing and a catalyst. The intermediate tritium concentrate is fed from the top of the column, and tritiated hydrogen is fed from below. Passing through the packing, the water is enriched with tritium as a result of the mass exchange processes occurring, while the hydrogen is depleted of tritium. The column is equipped with temperature sensors along its entire length. Pressure sensors are installed at the top and bottom of the column. From column K31, the tritium-enriched concentrate passes through a hydraulic seal to the top of hydrogen humidification column K32, which is filled with spiral prismatic packing. A constant temperature of 60 degrees centigrade is maintained in the column by electric heating. This column is designed to humidify the hydrogen coming out of the electrolysis cell. Pressure and temperature sensors are installed at the top and bottom of the column, and the column is also equipped with a humidity sensor. The tritium concentrate, with activity of 1 × 10 to the 11th power becquerel per litre from hydrogen humidification column K32, arrives at electrolysis cell feed tank K61, from which it is fed to electrolysis cell K81. Hydrogen from the electrolysis cell is fed at a flow rate of roughly 8 cubic meters per hour to the bottom of humidification column K32, and from there to the bottom of chemical isotopic exchange column K31. The hydrogen is depleted of tritium when it passes through column K31 as a result of catalytic mass exchange processes. The hydrogen from chemical isotopic exchange column K31 arrives at the bottom of wash column K33. This column is designed to wash the tritium out of the hydrogen prior to discharge, and the blowdown from the storage drums where gaseous hydrogen may be present is also sent to this column. The hydrogen from wash column K33 arrives at heat exchanger K201 for drying. The condensate from the bottom of heat exchanger K201 is returned to wash column K33. The hydrogen from heat exchanger K201 passes through flame arrestor K211, installed to prevent combustion of the volatile mixture to gas discharge manifold K231, from which it is discharged to the atmosphere. The activity of the tritium in the hydrogen discharged is monitored by dosimeters in the range from 200 becquerel per cubic meter and higher. Redistillate from tank K181 is fed to the top of column K33 to wash the hydrogen. After passing through the column, the water from the bottom of the column arrives at tank K271, where the activity of the tritium is measured. The water from tank K271 is returned to water distillation unit tank P11 to prevent discharge of radioactive water. Gaseous oxygen with a flow rate of roughly 4 cubic meters per hour from electrolysis cell K81 is fed to hydrogen burner K91, after which the residual hydrogen content in the oxygen does not exceed 0.05%. A start-up temperature of at least 250 degrees centigrade is maintained in the burner using an electric heater. After the burner, the oxygen is sent to return condenser K101 for cooling. The cooled oxygen arrives at wash column K111, in which it is cleansed of mist and entrained tritium concentrate droplets. After wash column K111, the oxygen is discharged through gas discharge manifold K141 to the atmosphere. Purified water is fed from water distillation unit tanks P101 and P102 to wash the oxygen. The water which has passed through wash column K111 is fed to tank K161. A line for sampling via a manual shut-off valve is provided here. The tritium activity is monitored in the line. Part of the hydrogen generated in electrolysis cell K81 is tapped at a flow rate of 12.5 litres per hour to tank K291 for subsequent fixation in titanium sponge. The hydrogen is fed from tank K291 via gas manifold K371, which regulates the flow rate, to adsorbers K301 and K302, which are installed in parallel and filled with zeolite. Final purification of the hydrogen prior to its fixation is performed in the adsorbers. After adsorbers K301 and K302, the hydrogen is fed to the hydration unit. It contains hydration vessels installed in parallel. The vessels are designed to conduct the reaction of tritiated hydrogen with the titanium sponge in the cartridge containers. Seven kilograms of titanium powder are loaded into a cartridge container and activated as follows. The assembled cartridge is placed in a shaft furnace, connected to a vacuum line, and pumped out by vacuum pumps K321 and K322 to a residual pressure of not more than 0.05 of a millimeter of mercury column. The furnace is heated to a temperature of 650 degrees centigrade. The cartridge is held under these conditions for 2 hours, then cooled to a temperature of 400 degrees centigrade, placed in one of the hydration units, and connected to the gaseous tritium sampling line. Sampling into one cartridge container is performed throughout the entire experiment. The second cartridge is held in reserve. The sampling is stopped when the pressure in the cartridge begins to rise. This completes the separation process. Together with the salts solidified in asphalt, the cartridge is sent for storage in accordance with the Ross-Rao standard procedure. The detritiation complex proposed to meet the needs of the Fukushima 1 nuclear reactor consists of 5 independent process lines. They are scaled according to the base module tested as part of the demonstration project. The separation and concentration coefficients are maintained. The capacity is increased to 480 cubic meters per day by simple staging. The complex is commissioned in stages. This makes it possible to begin processing tritium-containing LRW 6 months after construction begins. The project envisions 5 queues, each with capacity of 8 cubic meters per hour. Total construction time is 18 months. The complex occupies a footprint of not more than 2,500 square meters. The equipment is optimized for placement in a confined area according to radiation and fire safety codes and regulations. Flows of gaseous hydrogen are minimized, since the volume of water sent for electrolysis is reduced by a factor of 200 by using distillation in the first stage of separation. The structural elements and equipment are resistant to seismic effects. The electric power consumption of the complex is not more than 32 megawatts per hour. To treat tritiated water to 1,500 becquerels per litre, the height of the water distillation column will be increased by 9 meters, but power consumption will remain unchanged. Secondary radioactive wastes are not generated during operation. After processing 700,000 cubic meters of tritiated LRW, not more than 120 cubic meters of treated radioactive wastes in reinforced concrete containers will be obtained. Immobilization in the form of titanium titride guarantees safe storage of radioactive wastes throughout their potentially hazardous life.